You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
In last week's episode of Why This Universe, we talked about how space isn't what it seems. Space itself can curve and change shape. And not only that, but the curving of space around massive objects is actually what gravity is. Einstein's theory of general relativity says that space curves in the presence of matter and energy, and the curved space causes objects to take curved paths. And in last week's episode, we ended with Edwin Hubble's discovery that space is also expanding. Space itself is stretching out, and things in space are getting farther away from each other. In this episode, we talk about how to really conceptualize this idea of expanding space and what it can tell us about the very early universe. So the idea that space must be expanding or contracting comes out of general relativity. And while Albert Einstein was the person to literally invent general relativity, he was really opposed to this idea that space could be expanding. He even introduced a whole new term in his equation called the cosmological constant in order to make his equations predict a universe that wasn't expanding. His solution turned out to not be stable, and we know today that space is expanding. But back in the 1920s, it was still up for debate, and it was a really heated debate.
Now, in the history of science, very rarely does a debate as important or as contentious as this one get settled by theoretical arguments alone. Almost always these sorts of arguments get settled with new observations or empirical evidence that come in and show one side to be right and the other side to be wrong. And that's what happened here too. So I think to understand the discovery that space is expanding, we need to take a step back and understand how in the 1920s, the field of observational cosmology started and how that led to the discovery of expanding space. All right, so let me paint a picture for you. It's April 26th, 1920, and at the Smithsonian Museum of Natural History in DC, there was this really important debate. It was called the Great Debate. Two very famous astronomers, Harlow Shapley and Heber Curtis, were taking opposite sides of a position in front of a big crowd. The debate was basically whether the Milky Way, the galaxy we live in, is the universe, meaning really the entirety of the universe, or whether there are a lot of other things like the Milky Way out there, whether our galaxy was one of many. So as recently as 1920, this was like an open question. Like professional astronomers found themselves on either side. It was, debatable, I guess. There were some bits of evidence that both sides brought to bear on this. So Harlow Shapley, who was arguing that the Milky Way was really the entire universe, was everything there was, he would look at these things called nebulae, plural of nebula, and he said, well, these things are probably just small clouds of stuff in the Milky Way. And like, for example, there were measurements of something called the Pinwheel Nebula, which we would now call the Pinwheel Galaxy. And it had been measured incorrectly, it turns out, that it was rotating at a certain speed. And if it were a very, very far away from us and therefore very, very big, it would be rotating at faster than the speed of light. And we know from Einstein's theory that that's not possible. So it seemed to, in Shapley's opinion, prove that nebula was just a small thing somewhere in the Milky Way. Shapley also pointed out that some novae had been observed. So these are like exploding stars. They've been observed in certain nebulae that were, for a brief period of time, brighter than the entire nebula they resided in. And he just said that's not plausible that one exploding star could be brighter than a whole galaxy. All of the data that went into that was right, but it just turns out that sometimes exploding stars can be that bright. So his plausibility argument turned out to be wrong. Now, on the other side, Heber Curtis pointed out that the number of novae, these very, very bright stars in the Andromeda Nebula, now the Andromeda Galaxy, was about the same, actually a little bit larger number than those observed in the entire Milky Way. And that suggested, he argued, that the Andromeda Nebula was a big object similar in size and shape to the Milky Way. So in 1920, no resolution to this question came easily. Really, to settle it, what astronomers needed, was a new and more powerful way to measure the distance to a given object, like a nebula, a galaxy, whatever. If we could do that, we could find out if all these clouds that people are seeing in their telescope were local parts of the Milky Way or very, very distant galaxies in their own right. But at the time, there's just that sort of technique didn't exist yet. So the way that astronomers measure distance for very local things, very nearby things, is just using geometry, basically using trigonometry and observing things and looking at how stars move across the sky as, for example, the Earth rotates around the sun. But this only works for like the nearest handful of stars. And we call this parallax, by the way. And then to go to the next step, you need to look at the stars you can observe with parallax, notice things about their characteristics, in particular relating their brightness to their colors, and then looking at star clusters that are a little farther away and deducing how, what kind of brightness and therefore distance those stars are at. We call this main sequence fitting, and that works better, or at least to greater distances. But still, like, you can't get to any of the nebulae that way. It can only be used really, really locally. But then in 1908 and 1912, an American astronomer named Henrietta Leavitt wrote two really important papers on these objects called Cepheids. These Cepheids are pulsating stars, and she discovered for the first time, that there was a reliable relationship between how fast these things pulsated and how intrinsically bright they were. This meant that these Cepheids could be used as something astronomers call standard candles. By looking at their periods, you could deduce how bright they were, and by measuring how bright they appeared to be, and knowing how bright they actually are, you can work out how far away from us they are. So Leavitt basically gave us the first tool to measure the distances to things like galaxies.
So Henrietta Leavitt invented a new way to measure how far away distant objects in space are, more distant than we ever had access to before her. Unfortunately, Leavitt died young, at the age of 53 in 1921, so she wasn't alive to see the brilliant outcomes of her discovery. But her work ultimately led to the answer to this debate about whether the Milky Way is the only galaxy in the universe, or if it's one of many.
Other people followed up on her work, in particular Edwin Hubble, the famous astronomer. The Hubble Space Telescope is named after him, for example. And his assistant, Milton Humason, who was an expert astronomer in his own right, were using Leavitt's technique to measure the distances to as many Cepheids as they could in various nebulae. They were using something called the Hooker telescope, which at the time was like the biggest telescope in the world. It was a 100-inch reflector in the Mount Wilson Observatory in California. And this wasn't just like a telescope that was a big deal for a little while. It was the biggest telescope until 1949. So this is the big dog in astronomy for a long time. And Hubble and Humason had access to it. And they started to measure that these Cepheids that they were observing in these objects were really far away. Like, they measured some in the Andromeda Nebula that they found to be 900,000 light years away, which is way bigger than the size of the Milky Way. It turns out that they actually underestimated the real distance. It's more like 2.5 million light years away. But they got the main point right, though, that these Cepheids weren't in some local cloud of gas. The Andromeda Nebula isn't a nebula at all. It's an entire galaxy about as big in size and scope as the Milky Way. So I like to think of this transition as a kind of a continuation of the Copernican revolution. So Copernicus, made the argument correctly that the Earth isn't the center of the solar system. We're just one planet of several orbiting around a star. And then later we learned that our star isn't special. It's one of many in the Milky Way. And then in the 1920s, this continues by learning that the Milky Way isn't particularly unique or special. It's just one island universe of many, 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 something like 1 trillion in the observable universe that occupy space and time.
So do you think our next step is learning that our universe is just one of a multiverse?
I would just say it would be weird if it turned out that our universe is the only one. So up until this point, the incredible discoveries are being made. We're learning that the Milky Way isn't the only galaxy, and these objects that we're observing with our telescopes are very, very far away. But this hasn't told us anything about whether this, space that makes up our universe is expanding or not. That hasn't been figured out yet. But then there was this other technique that was kind of pioneered by this American astronomer at the Lowell Observatory in Arizona. Vesto Slipher was his name. And in 1912, he carried out a bunch of measurements of galaxies using the redshifting of their light. It's kind of like the Doppler effect for light as predicted by Einstein's theory, to work out how fast they're moving either toward or away from us. So how fast they're moving along our line of sight to them. What he expected is that, roughly half the galaxies would be moving towards us and roughly half would be moving away. Just like if you looked up in the sky and measured the speeds of different molecules moving around, you just expect them to kind of be moving around in random directions. But he didn't find that. He found that almost all of them were moving away from us. In other words, the light he was observing from them was being shifted to lower frequencies, or what we call redshifted. And he didn't really have an explanation for this, I think. But then as time advanced and more of these measurements were made, Hubble and Humason in 1929 combined their catalog of 46 different galaxies, all with measured distances, with the velocities that Slipher had already measured. And they plotted them together. And on this famous plot, they found that there was an approximate proportionality between the distance to a given galaxy and how fast it was moving away from us. The farther away a given galaxy is from us, the faster it was receding. This is called Hubble's law. The modern value of this proportionality constant is about 70 kilometers per second per megaparsec. There's actually a lot of controversy right now about whether it's like 67 or 73. Different ways of measuring or inferring this quantity seem to get different answers. It's possible that what that's telling us is that somebody's measuring it wrong. It's also entirely possible that there's some sort of new physics afoot impacting how the universe was expanding or otherwise evolving in the first, say, 100 or few 100,000 years after the Big Bang. A lot of ink has been spilled, including a lot of my own, on that very point of debate, but roughly 70, we'll say, which translates to about 50,000 miles per hour for every million light years between us and a galaxy. So if I take a galaxy 1 million light years away from us, that would be moving away from us at 50,000 miles an hour. If I look at a galaxy 1,000 million light years or a billion light years away, that galaxy would be moving at 50 million miles an hour away from us. So what this tells us is not just something specific about galaxies, but something about space and time. In particular, it says that if you take any 2 points in space, those 2 points in space will be moving apart from each other. The amount of space between them will grow as time advances. That's what Hubble's observation really taught us.
So you could first imagine that the universe is expanding like the surface of a balloon does when you blow it up. If you draw any 2 dots on the outside of a balloon, those 2 dots will move away from each other as you blow into the balloon and it expands. But the difference here, and the thing that can be so hard to grasp about space expanding, is that unlike the balloon, which expands into the surrounding air, the space of our universe isn't expanding into anything else at all.
If there existed something that space could expand into, I would have just called that stuff space. And that's not what I mean. I mean, all of space is growing as time advances, not just some of it. We're not just having these galaxies move somewhere else. The space they occupy is getting bigger as time advances. So, to better understand what I mean for space to be expanding without it expanding into some other space or something else, consider an analogy. So, this analogy is not meant to describe the real expanding universe, but just to kind of understand what it might mean for space to be expanding. Imagine that I'm sitting here in my home office, or my COVID office where I do most of my physics these days. So the size of this room is about 12 feet from wall to wall. So let's say I wanted to find out how big this office is. So I take a ruler and I lay 12 of them side by side, and I conclude, okay, my office is 12 feet long. Okay, good. And then I wait a while and I make the measurement again in exactly the same way, but this time it takes 13 rulers to go from wall to wall. I can interpret this data in two very different ways. I could say, okay, well, I just learned that the room is getting bigger because it was 12 feet long and now it's 13 feet long. So it's growing at a rate of 1 foot per whatever length of time it was between the two measurements. Or I could say, well, perhaps the room is staying the same and my ruler is just getting smaller at some steady rate. And you couldn't tell these two things apart from each other. Well, that's not strictly true because I could always compare that ruler to other things in the room and see if they were the same ratio or same comparative size. But let's say everything in the room were shrinking in unison together, including myself and including things like the speed of light and the size of atoms, everything you could ever measure. You would not be able to tell from inside my room whether it was getting bigger or whether everything in it was getting smaller. So we can do this with the universe. So if you're not comfortable or struggle with conceptualizing space getting bigger without moving into something else, you can instead just imagine all the stuff in space, again, including things like the speed of light and the size of atoms, are all shrinking in unison. Now, do I think that's what's really going on? Well, no, it would be really contrived and a bunch of coincidences would have to be cooked into the laws of physics somehow. But it's a good mental trick to help you conceptualize the idea of expanding space.
So we know that right now, space is expanding and getting bigger as time goes on. And so if you play the tape backwards, you'd see that space used to be a much more dense and compact thing. So the expansion of space helps us learn a lot about what the universe used to be like a long time ago. And it turns out that the universe used to be a much different place than it is now. But to see that, let's think about what the universe is made up of. You could divide the contents of the universe into two categories, what we think of as matter, the atoms and particles we're used to hearing about, and radiation, stuff like light. Okay, so there's actually a third category, something called dark energy, but we'll get to that one next week. So these different categories each respond to the expansion of space a little bit differently.
So if I take a piece of space that contains some matter and I have that space expand, so the volume now gets much bigger, the density of that matter will go down as that volume increases. So if I take a piece of space and I make it 10 times longer from one side to the other, so the volume now grows by 10 cubed, by a factor of 1,000. And that means the density of matter in it goes down by a factor of 1,000. So in the past, we can conclude that our universe must have been much more dense than it is today. You can do the same thing with light or other kinds of things moving at speeds close to the speed of light, stuff that cosmologists call radiation. And they get the same sort of geometrical dilution that matter gets, the same factor of 1,000 when space expands by 10 in any given direction. But in addition to that, the waves of that light get stretched by the expansion of space. And when you stretch the wavelength of light, you lower its energy. So instead of going like a factor of 1,000, instead of decreasing in energy density by a factor of 1,000 like matter would, Light and other forms of radiation get diluted by a factor of 10,000. So instead of 3 powers of the size, 4 powers of the size. So that means that if you go back farther in time, not only was the universe denser, but a larger proportion of its energy was in light and other forms of radiation. And no one knew at the time, but no one knew how far back you'd have to go for this to be true at the time. But if you go back far enough in time, there was inevitably a period of time where radiation, light, and other forms of radiation made up most of the energy in our universe. It turns out that was around 50,000 years after the Big Bang, but no one knew that at the time. But the idea that there was a light or radiation-dominated era of our early universe's history came directly out of Hubble and Humeson's observation that the universe was expanding.
A radiation-dominated era in our universe would be pretty unrecognizable from what we have now. No stars, no planets, instead just energetic photons zipping all around and bumping into each other. Eventually, as the universe expanded, this era ended, but the remnants of it are stuck forever in what we call the cosmic microwave background, or the CMB. In 1964, Penzias and Wilson observed the light from the CMB for the first time.
And we can also be confident that there was a radiation-dominated era in the early universe based on the amounts of light elements, light chemical elements in our universe. So in the first seconds and minutes after the Big Bang, well into the radiation-dominated era, the entire universe was at something like 1 billion degrees. And at this temperature, nuclear fusion could be very, very efficient. So you can think of the entire universe as being a giant efficient nuclear fusion reactor at that time. And in those minutes and seconds after the Big Bang, most of the protons and neutrons experienced a variety of nuclear reactions. About a quarter of the mass in those protons and neutrons was fused together into helium. Small amounts are made into things like deuterium and lithium and beryllium. And we can use the equations of the Big Bang theory and Einstein's relativity combined with nuclear physics to calculate how much of these different elements should have been formed. And those predictions match the observations very, very well. So we're pretty sure, we're extremely sure, in fact, that our universe did expand out of a hot, dense, radiation-dominated early universe over about 13.8 billion years.
This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago, and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.